joint work I have. Okay, recording in progress. Yeah, this is the joint work I have with my supervisor, Alberto Marcone, which is about the descriptive complexity of Fourier dimension and the study of Salem sets. So let me start by giving you some motivation for the work. Well, okay, so this work is on the boundary between descriptive set theory, so descriptive complexity of sets, and fractal geometry. So we're going to talk about Hausdorff and Fourier dimension. Well, Hausdorff dimension is relatively standard notion. I guess like most of you already met this notion sometime during the grad or undergrad studies. Hausdorff dimension is a way to estimate the size of a null measure set by means of open covers of the set itself. There's an effective counterpart of the Hausdorff dimension, which can be, well, the formal definition may vary from textbook to textbook, but the idea is that you can talk about like effectively presented open covers or in terms of martingales. Details are not really going to be relevant for us now, but the point is that if we restrict our attention to singletons, then the effective Hausdorff dimension of a singleton can be characterized by means of the Kolmogorov complexity of the point itself. So this establishes a nice relation between the Hausdorff dimension of points and purely, say, computability theoretic notion, which is the one of Kolmogorov complexity. And this was used recently by Lutz and Lutz, who proved a point-to-set principle, which links the classical, so the standard Hausdorff dimension of a set, with the effective dimension of its points. So, well, this is the formal statement. It says that, well, the Hausdorff dimension of a set depends in some way, which I'm not gonna like expand further. In some way, it depends on the complexity of the points lying in the set. So this raises a somewhat natural question, which is like, can we do something similar for the Fourier dimension? Well, of course, similar here is rather vague, but the idea is, can we connect somehow the Fourier dimension? Can we do some sort of exploration of the properties of the Fourier dimension of a set by means of, say, computability theoretic properties of its points? So this is very general, and this work goes in this direction, trying to explore the properties of the Fourier dimension itself. So okay, let's start with let's give some definitions now. I'm not going to give the full formal definition of Hausdorff dimension, also because it's relatively involved. There are a bunch of soup and inf to take, and it's not really like, it's not extremely relevant for us now, so I'm just going to skip it. As I said, the idea is that you want to cover your set by open sets, and then you want to minimize the sum of the diameters of the sets that are in your cover raised to a certain power, and you want to somewhat minimize this quantity in order to, you know, get an estimate of the size of a set. What is going to be relevant for us is instead a characterization of the Hausdorff dimension that works for Borel subset. Well, Borel subsets of the Euclidean space. So this is a consequence of Frostman's lemma, and allows us to say that the Hausdorff dimension of a set can be written in terms of the existence of a probability measure here supported on the set, such that, well, okay, there exists a constant such that for every x and for every point and every radius, the measure of the ball decays with a certain rate. So it's less than or equal to a normalization constant here, and then the radius raised to a certain power. Now what this implies is that the measure, for example, cannot have atoms, right? It has to be continuous. And this is implied by this last condition here, simply because if a measure has an atom, then the measure of a ball cannot decrease with the radius itself. So this like what this is saying is that there's a connection between the Hausdorff dimension and, well, this is actually, if you're familiar with it, it's the definition of the capacitary dimension. And the Frostman's lemma pretty much says that for Borel sets, the two notions agree. And this is actually the characterization of the Hausdorff dimension we will be working with. On the other hand, the less familiar notion probably is the one of Fourier dimension. So let me start by giving the definition of the Fourier transform of a measure. So for every finite Borel measure mu, we can define mu hat here, which is the Fourier transform of a measure, which is defined as the integral over the whole space of, the standard Fourier exponential here, where the dot here is just the scalar product between points in the Euclidean space. And, well, it's integral with respect to the measure. Now, the details, again, may change a little bit from textbook to textbook. Somebody asks for a normalization constant here, or like the 2 pi in the exponent. The details don't really matter that much for us, so we just stick with the definition, which is the simplest to write. So this notion, like the definition of Fourier transform of a measure, allows us to talk about the Fourier dimension of a set. We define the Fourier dimension of a set for a subset of the Euclidean space as the supremum of all S between 0 and D, where D is the dimension of the space, such that, again, there is a probability measure supported on the set, and well, there is a constant here such that for every point, the Fourier transform of a measure of the measure mu decays with a certain rate. Now, it's not super easy to give like an intuitive idea of what's going on here, like in a couple of minutes. But let me just say that, okay, this characterization of the Hausdorff dimension says that there must be a measure supported on the set, which has to be continuous, and, well, it has to somewhat be regular, but not that much. Like this condition is rather mild, if you want. While the condition on the decay of the Fourier transform is much stronger, because it not only implies that the measure has to be continuous, because the Fourier transform of a measure which has an atom cannot decay, but also that the points of the set has to be somewhat uniformly distributed. So there has to be some sort of the set has to be like relatively sparse in the unity interval or whatever we're considering. Okay, so the exact exponent here may look weird at first. There seems to be no reason why we actually choose minus s half here. And indeed, the reason is just technical, and it's because it allows us to prove the following relation between the Fourier dimension and the Hausdorff dimension. And in particular, for Borel subsets of the Euclidean space, we have that the Fourier dimension never exceeds the Hausdorff dimension. The two notions can agree, in which case we say that a set is a Salem set. So a Salem set is essentially a set for which the two notions coincide. And in this case, we just talk about dimension. We don't really need to specify Hausdorff or Fourier dimension because they're equal. So let me give you a few examples of Salem or non-Salem sets. just to have an idea of what's going on here. Well, okay, so trivial examples. The empty set is Salem, of course, because its house of dimension is 0. The full unit interval is Salem when seen as a subset of 0, 1, just because it's a whole space. And of course, it has to have full dimension, both Fourier and the house of dimension. Cantor middle third set is not a Salem set, and this actually like helps a little bit in having an intuition of what it means to be uniformly distributed for a set, right? So it's known that the house of dimension of Cantor middle third set is strictly positive, but its Fourier dimension is 0, and that's because like if you like intuitively you can think about it as the Cantor set has very regular holes. So the points in the Cantor set are not very well distributed over the interval. Like they have like not only there are holes in the Cantor middle third set, but they are very regular and the points are very sparse. And so yeah, this is like to have positive Fourier dimension, this cannot happen. You need to be somewhat uniform in some sense. Giving a deterministic, like an explicit example of a Salem set is not extremely easy. First examples of Salem sets were random constructions, which means that Salem built a family of sets, which with probability 1 they were Salem, but of course you cannot just like pinpoint a single set and say that okay, this is Salem with a certain dimension. One of the first examples of an explicit Salem set is called Jarnìk's fractal. This is a set that comes from Diophantine approximation of real numbers. So for every alpha greater or equal than 0, you can define the set of alpha well approximable numbers as the set of, well, this is the formal definition, right? It's not going to be extremely relevant for us. This is just saying that you can, like, there are infinitely many rationals, if you want, such that they are close to your point, where close can be made precise by this relation. So again, it's not like we don't really need to understand in full detail the Diophantine approximation of real numbers. What we need to know is that this set is Salem with dimension 2 over 2 plus alpha. The fact that this is the house of dimension was the result by Jarnìk and Besikovic independently, and then years later, Kaufman showed that the Fourier dimension actually matches the Hausdorff one. For alpha equals to 0, you actually get that, well, the 0 well approximable numbers are actually every real number. So this is Dirichlet's theorem, and therefore, like, of course, in case of alpha equals to 0, you get a Salem set with dimension 1. So let me just point out. So what we need to underline for this set is that, well, of course, this is one of the first examples of Salem sets, so it's going to be important for us, but it's a pi03 set. It's not closed. It's actually dense in the unit interval, but it's not closed, of course. It's not like that for every alpha you get the whole interval. We will be mainly working with closed sets, so this is actually not going to be extremely interesting for us per se. But if we take a closer look at the original Kaufman construction, well, he proved that there's a closed subset S alpha of E alpha, which is actually Salem. And well, it's Salem with the same dimension. So it showed that this set has the prescribed Fourier dimension. Another thing I want to point out before moving on is that S alpha can be written as the infinite intersection of, well, what I wrote GK here, well, these are just finite unions of closed intervals. So it's just saying that, well, okay, of course, closed set can be written as the infinite intersection of closed sets, but in particular, it can be written as infinite intersection of finitely many of unions of finitely many closed intervals. And if you think about it, this is pretty much what happens with the Cantor set, right? You start with the unit interval, and then you start removing open sets which are contained in the complement. And this is a general thing, like this holds for every closed subset of the unit interval or the Euclidean space. So, okay. So we're now ready to actually state the question we're going to answer. This was asked by Ted Slayman during the grad summer school in logic in Singapore back in 2018. He asked about, like, he suggested as an open problem to characterize the descriptive complexity of the family of closed Salem subset of 0, 1. Yeah, okay, so this is like the question we tried to answer and what we actually answered. So let me just try and be more precise about what it means to characterize the descriptive complexity. So we will locate the family of closed Salem subset of 0, 1 within the Borel hierarchy. We will show that we will like prove that it lies at a certain level of the Borel hierarchy. Well, this is usually done, like a standard technique is use the wedge reducibility to prove this. Let me just quickly give the formal definition. So for every x and y, for every Polish space is x and y, a subset A of x is said to be wedge reducible to B subset of y if there's a continuous map from x to y such that x is in A if and only if f of x is in B. Or equivalently, you can say that the pre-image of B is exactly A. Now that you have, okay, so given the notion of reducibility, well, it's relatively like we can induce a notion of hardness and completeness in a relatively standard way. So we say that B is gamma hard if for every A in gamma of the Cantor space, and the Cantor space here is just fixed for convenience, we have that A is wedge reducible to B. So in some sense, it's as complicated as every gamma set. And we say that B is complete if it is gamma hard, and B itself is in gamma of Y. Okay, so usually when trying to characterize the descriptive complexity of a family, what you do is you prove that you have an upper bound, and then you show that the upper bound is actually tight, so that they actually belong to that level of the hierarchy. We will be working first in the unit interval, so we will just consider closed Salem subset of 0, 1, and therefore we will be working in the hyperspace of compact subsets of 0, 1. Now, this space K here is canonically endowed with the Vietoris topology, or if you want, by with the topology induced by the Hausdorff metric. So the first, like the upper bounds we get are that for closed subsets of 0, 1, the condition the Hausdorff dimension is strictly greater than a real between 0 and 1 is actually a sigma 02 set. And it's actually a sigma 02 condition. And similarly, saying that the Hausdorff dimension is greater or equal than a real is a pi 03 condition. And the same complexities hold for the Fourier dimension. Now, let me just quickly give you a brief sketch of how the proof goes. So we will just prove the statement for the Hausdorff dimension, and well, the proof for the Fourier dimension is very similar. By means of Frossman's lemma, again, like as I said, we will be working with this characterization of the Hausdorff dimension. And so we have that the Hausdorff dimension is actually the supremum of this set. I just copy and paste the definition given by, like the characterization given by the Frossman's lemma. So This condition here is a closed condition, is a pi01 condition. This is just an exercise in Kekri's book. This again, so if you also consider these two universal quantifier, well, you're still pi01 because this is just the intersection of closed sets and you're still closed. If you factor in also the quantification on the quantification on the constant, you get a sigma 02 condition because you can just restrict yourself to rationals. And now you have an existential quantifier over a Polish space. So this is in general would be a sigma 1 condition, but actually since the inner set here, inner condition here is a sigma 02, and the ambient space 01 is compact, we actually get that the hyperspace of probability measures supported on a compact set is a compact space. And the projection of a sigma 02 along a metrizable and compact space is again sigma 02. So we actually have a significant drop in the complexity, and therefore we have that this whole set is actually a sigma 02 set. Call it dA, right? So the dimension of A, the Hausdorff dimension of A is just the supremum of a sigma 02 set. Well, now the proof is over, right? Because we can just because saying that the supremum of a set is greater than P is it's equivalent to say that there exists some rational which is strictly greater and belongs to the set. So you're again sigma 02, and saying that the supremum is greater or equal than P, well, it means that every rational below P is in dA, and therefore you get an extra universal quantifier here, and you end up in pi03, like the complexity ends up being pi03. So again, the very same proof goes for the Fourier dimension. The only difference is like in the inner part, but as long as you prove that the inner part is pi01 again, then the rest of the proof follows. So using this result, we can also get the upper bound for the family of closed Salem subsets of 01. The proof like is just 3 lines, so we can quickly give it. Again, since we're working with closed and therefore Borel subsets of the Euclidean space, one inequality is always true. So we only need to say that the Hausdorff dimension is less than or equal than the Fourier dimension. And therefore, this is just like saying that for every rational, whenever the Hausdorff dimension is greater than a rational, then also the Fourier dimension is. And therefore, like this is sigma 02, this is sigma 02, and the whole condition is pi03. So we get an upper bound also for the complexity of the condition being Salem within, being a Salem subset of 01. So let's now turn our attention to the hardness result, because we just proved the upper bound. Now we need to show that the upper bound is actually tight. So the key tool for proving the hardness is actually this lemma here. So this lemma says that for every p in 01, there is a continuous, and in fact, it is actually a computable map, fp from the Cantor space to this set of Salem subsets of 01. So we will always be building a Salem set, and such that the dimension of the image of a point is P if and only if X belongs to Q2, where Q2 is just a fixed sigma 02 complete subset of the Cantor space. And otherwise it's 0. So the idea of this proof, let me just quickly give you the idea, is that we can basically so the set Q2 here we are considering is the set that of points that have finitely many ones. So the idea is that each time you see a 1 in your input, you shrink your set and control its Hausdorff dimension in such a way that if infinitely many ones appear, then you end up with the set with null Hausdorff and therefore Fourier dimension. Otherwise, you just pretty much continue the construction from a certain moment on. You will just continue a construction that eventually leads you to Salem subset of 0, 1 with a prescribed dimension. So this lemma immediately yields the completeness for the condition being strictly greater than real for both the Hausdorff and Fourier dimension, but actually it can be used for proving that also that you get the completeness also for the greater or equal conditions and the condition of being a Salem subset of 0, 1. So all these three sets are complete are pi03 complete. Again, let me just quickly sketch a proof of this fact. So we start from a fixed pi03 complete subset of the, well, it's not really the Cantor space to be precise, right? But it's a set of double sequences. You can think of it as the Cantor space in a canonical way. So we want to show that we can map X to a Salem set if and only if X belongs to P3. So P3 is just a set of sequences that in each row they have only finitely many ones. So you can given X, you can always modify it in a computable, super uniform way. You can modify it in such a way that if a certain row has infinitely many ones, then so do all the next ones. This is just to make the presentation easier. It doesn't really affect the proof. So consider split your unit interval into countably many disjoint intervals, closed disjoint intervals, and well, what you do is you build a fractal within each of these intervals according to the corresponding row. So, well, actually, you say, okay, in the first interval, you build a set which is not going to be Salem and has some large Hausdorff dimension and some small Fourier dimension, whatever you like. Then what you do is in each of the following interval, you build a Salem subset. So you build a Salem subset Si+1 within Ti+1 according to the ith row of X in such a way that, well, the dimension of the sets you build goes to 1 in the limit. So if the ith row of X has finitely many ones, then you, sorry, this is supposed to be minus. So the dimension has to go to 1. So this has to be 2 minus I+1. But so the point is that if every row has finitely many ones, then in the limit you go to 1 and you end up with the Salem subset of 0, 1 with dimension 1. Otherwise, at a certain, at the finite stage, at the finite row, you will get that all that row and all the following ones will have infinitely many ones, and therefore the overall set will have Hausdorff dimension 1, but Fourier dimension something which is strictly smaller than 1, and therefore you end up not being Salem. Right, so this proves that that being a Salem set is pi03 complete condition, and therefore Salem sets are pi03. It's a pi03 subset of the closed or compact subsets of 0, 1. So how about can we generalize this result to higher dimension? So to case of 0, 1 to the d for some fixed d. Well, the problem when you try to generalize this kind of results is that Fourier dimension doesn't really behave very well. It's not very stable as a notion. So the upper bounds are the same because the upper bounds were just based on the complexity, on the compactness of the ambient space. But the problem is that the lower bounds now are, the problem is that if you take a subset of 0, 1 and you see it as a subset of 0, 1 to the d, then its Fourier dimension drops. In general, every subset of an m-dimensional hyperplane with m strictly less than d will have Fourier dimension 0. So this is just saying that, well, some curvature is needed in order to have positive Fourier dimension. So what do we do now? We cannot just hope to build a Salem set in 0, 1 and expect it to be Salem when seen as subset of 0, 1 to the D. Well, so what do we do? Well, there are a couple of options. In the end, we thought that the better one was to exploit a recent construction by Fraser and Hambrook, who showed that for every alpha greater or equal than 0, there's a say higher dimensional analog in some sense of the Jarnìk's fractal. So this is this EKB alpha. I'm not giving the definition because it's not going to be relevant for us. But the point is that this is a Salem subset of dimension 2D over 2 plus alpha. So pretty much they are building a Salem set of every dimension from 0 to D, which is a subset of 0, 1 to the D again. So, well, again, the exact definition is not really relevant. What is important for us is that it is built in a very, it's very similar to Jarnìk's fractal. So our ideas can just be generalized to 0, 1 to the D just by mimicking what we did in the one-dimensional case, but now using this EKB alpha instead. And therefore, we can, we have a higher dimensional analog of our lemma before, and we have that for every P in 0D, there's a continuous and indeed computable map FP, witnessing the fact that that having a large Hausdorff dimension is sigma 0 to complete pretty much. So again, the dimension, both Hausdorff and Fourier dimension of the image of our map is going to be P if and only if our set lies in some sigma 0 to complete subset of the counter space. And then again, using this tool, this is just mimicking all the strategies we've done in the one-dimensional case, but just of course, with the due modification, we can just reobtain the complexities we got for the one-dimensional case. And therefore, again, having Hausdorff or Fourier dimension strictly greater than P is a sigma 0 to complete condition, while having Hausdorff dimension or Fourier dimension greater or equal than P is pi 03 complete, and being Salem is again pi 03 complete. So what about the full Euclidean space? What can we say about relaxing the compactness of the ambient space? How do things change if we move to RD instead? Well, now the problem is not going to be the hardness anymore, because the both Hausdorff and Fourier dimension are preserved when we take a subset of 0, 1 to the D and we see it as a subset of R to the D. Therefore, the hardness just follow from the previous results. The problem now is, of course, it's actually the upper bounds, because the upper bounds, if you remember, were based on the fact that the ambient space was compact, and now we don't have the compactness anymore, so we need to be a little bit more careful. So let me just start off by saying that, by discussing the topology we put on the hyperspace of closed subsets of R to the D. In general, there's no canonical choice. So while for the compact subsets of 0, 1, the Vietter's topology is somewhat standard. For the hyperspace of closed subsets of RT, well, it's not really that obvious which is the right topology. So we consider both the Vietter's and the Feld topology. Let me just discuss a little bit why these two. Well, the Vietter's topology is maybe the more familiar one, and this somewhat is the same, quote unquote, the same topology we put on the hyperspace of compact subset of 0, 1 to the D. If you want, it is again induced by the Hausdorff metric. The problem is that the Hausdorff metric is not really a metric anymore. There can be sets which are infinitely distant from each other, and so and indeed this highlights the more delicate point, which is that the Vietri topology is not metrizable, let alone so in particular the hyperspace of closed subsets of R to the D with the Vietri topology is not a Polish space. This is very annoying, also because we asked that, like when we gave the definition of hardness and completeness, we asked that we were working with Polish spaces, right? So in case of the Vietri topology, we cannot really say that the Salem subsets are pi03 complete, because like it makes no sense by definition. On the other, like, of course, you can still talk about the wage reduction, but you cannot really say that that the set is complete or hard for like when talking about the Vietri topology. On the other hand, the Feld topology looks way nicer. The topology is polished. Not only is polished, but it's also compact, and it generates a standard Borel space, so looks pretty nice. Like the downside, if you want, is that it's coarser than the Vietri topology, and therefore, like continuity with respect to the Feld topology is less informative than continuity with respect to the Vietri topology. So in the end, we consider both of them. I will actually like implicitly consider only the Feld topology, because it's just easier to say that some family is complete or hard or whatever. But keep in mind that all the results actually hold also for the Vietri topology. So so instead of thinking about completeness, you just say, okay, they are wage equivalent if you want, but whatever. So the continuity of them. So what I mean is that the continuity of the map holds also for the also if you consider the Vietri topology. Okay, so this was the first problem, the topology on the hyperspace of closed sets. The second problem is that the Fourier dimension, well, as we mentioned already, is very unstable as a notion. Sometimes it's very painful to work with. One problem is that in general, it's not so-called countably stable. So the Fourier dimension of a union is not necessarily the supremum of all the Fourier dimension of the pieces making the union, let's say. And also it's not so-called inner regular for compacts. So it means that the Fourier dimension of a set is in general not the supremum of the Fourier dimension of the compact subsets of your set. And well, indeed, there's a counterexample for both of them. There's an F sigma subset of 0, 1, so union of compact sets, and G is a subset of 0, 1 with Fourier dimension 1, but such that every Kn has Fourier dimension 0. So things looks pretty bad, but actually, so we proved this sort of weaker irregularity condition. We proved that for every point class gamma, and like every A in gamma of the Euclidean space, for every A in gamma of RT, we can characterize the Fourier dimension of A by means of the supremum of the Fourier dimension of K, where K is now, well, it's bounded, it's a bounded subset of A, but now it's, well, not closed, is in general, but it's just gamma of RD itself. So in particular, this implies that in our case, where we're working with closed sets, so gamma for us is pi 0, 1, this means that we actually have irregularity for compacts in case of, well, when working with closed sets, right? Because you're bounded and closed, and therefore you're compact. And this is basically what we need to sort of run again the argument to estimate the upper bound. Like recall that now we only have to prove that the upper bounds are actually sigma 02 and pi 03 respectively. And this result allows us to sort of run the argument again, and therefore obtain again the same complexities for both the Hausdorff and Fourier dimension, and again for the condition of being a Salem subset of R to the D. The complexities are again sigma 02 and pi 03 respectively. So in the last few minutes, let me just give you a very brief overview of how these results can be used, like the effective counterparts of these results. So basically, what happened is that when we did all of this, then we looked back, and we looked back at like all the results we proved, and we were like, oh, look, everything is actually effective. There's nothing, well, there are a few weird things going on, but if you carefully inspect the details, you see that everything is actually computable. So, so we actually have that all of these conditions are not only complete for the bold phase case, but also for the light phase case. So they are light phase complete with respect to like like respectively to the complexity we estimated in the bold phase case. So yeah, so every completeness result is actually a completeness result from the point of view of the light phase parallel hierarchy. How can we use this? Well, okay, so this is a standard notion. We say that F is sigma 0k measurable if and only if, well, pre-images of open sets are sigma 0k relatively to the domain of F. The effective counterpart of this result is that, well, you say that F is effectively sigma 0k measurable, or you say that it's sigma 0k computable if the pre-image of an open set can be uniformly computed from a name of the open set itself. So the results we had on the light phase completeness imply that both the Hausdorff and Fourier, the maps that compute the Hausdorff and Fourier dimension are effectively sigma 03 measurable. So this per se is a result, like this locates the maps in the Bayer hierarchy, but we can do something more, and we can show how this result can be used to characterize the Weihrauch degree of the maps computing the Hausdorff and Fourier dimension. So again, I'll be very quick. This is not going to be like a full talk on Weihrauch reducibility, so I will just give you a hint of what Weihrauch reducibility is and how to complete the argument. So Weihrauch reducibility is a notion of reducibility between multi-valued functions on represented spaces. Now, a represented space is just saying that, well, you have a set and you have a way to assign names, which are elements from the Bayer space, to elements of X. So you just say that you have a surjection from the Bayer space to X, and the pre-image of an element in X is just the set of name of that element. If F and G are possibly partial, well, multi-valued function, which means that, well, just means that they can have multiple outputs, we say that F is Weihrauch reducible to G. And well, I mean, I know that this creates a little bit of confusion with the wedge reducibility, but forget about wedge reducibility now and just consider, like, we will just be talking about Weihrauch reducibility for the remaining few minutes. We say that F is Weihrauch reducible to G if there are two computable maps that work as follows. So I give you a name of an input of F. You apply phi to that name, and so computably obtain a name for an input of G. Now you use G as an oracle. G produces, like, intuitively produces a name for a solution, and after that you use psi as a post-processing phase to compute a name for a solution of X, given a name of X itself and a name for a solution. So intuitively, you can think of a Weihrauch reducibility to say that you can solve F using G as an oracle only once. So you start from an input for F, then you compute a question for the oracle G, then you call the oracle, it gives you an answer, and with that answer, you compute a solution for F, for your original input. Now, there are many ways to combine problems together. So the idea of calling the oracle more than once, or calling separate oracles in parallel, and so on and so forth. I just want to highlight this particular operation, which is the compositional product, which intuitively captures the idea of applying G first, then do some computable operation with the output, and then use this output to compute the question for G, and so apply F, and then get the solution. Intuitively, so again, it's just saying, it's like saying, okay, you can use first an oracle G and then an oracle F. And if you want to use like the oracle F n times, we just write F to the n this way. So let me show you how we can use our result to compute the Weihrauch degree of the map computing the Fourier dimension. So there's this very nice result from Vasco Bratka, which says that the problem lim of computing the limit in the Baire space. So I give you a Cauchy sequence in the Baire space, find its limit. This is in some sense the most complicated effectively sigma 0k plus 1 measurable problem. So formally, the result says that F is Weihrauch reducible to lim k, so k iterations of lim, if and only if the map is effectively sigma 0k plus 1 measurable. Now, lim k is not really clear what it is. One loses intuition rather quickly. So you can think of it as the problem of answering countably many sigma 0k questions in parallel. I give you countably many sigma 0k questions, and you have to answer 0 or 1 for each of them. So let me conclude with this very short proof of the Weihrauch equivalence between the Fourier dimension and lim2, actually. So one direction, again, follows from the result by Bratka, because we said that the Fourier dimension is effectively sigma 0.3 measurable, and therefore reduces to lim2. The other direction, well, this is what we do is, okay, you're given a sequence of elements in Cantor space, and you want to answer for each of, you want to know for each of them whether they belong to, the fixed sigma 0.2 complete subset of the Cantor space. So what you do is you start from this sequence and you build a Salem subset of 0.1 to the d. I'm not going to give you the full details of how the construction works, but the idea is that its dimension, both Hausdorff and Fourier dimension, encodes all the answer to all the question you asked, in such a way that from like knowing the Fourier or Hausdorff dimension will actually allow you to compute the answer to all of the questions. And this pretty much shows how this pretty much concludes the Weihrauch equivalence of the two maps. Right, so I leave you with a few references, and thank you very much.
Yeah, so let's thank the speaker for his talk. Thank you, Manlio. Are there any questions? So please just switch on your microphone and ask a question if you have any.
I have one. You'd mentioned at the start for your concrete example of a Salem set that I think that was pi03, but you could find a closed Salem set inside.
Yeah, right.
And then you had also pointed out that compact regularity generally fails.
Right.
Does it fail in a sort of, does it fail in a very bad way, or is it like always true that a Borel Salem set contains a closed Salem set of the same dimensions?
That's a good question. Okay, so in general, let me think for a second. So what I'm thinking right now is that you may have, okay, what I'm thinking right now is that on the one hand, the Fourier dimension is defined by means of the existence of some measure supported on the set, right? So the support of a measure is always closed. And therefore, like every measure witnessing that your dimension is at least S, witnesses that there's a closed subset of your set which has at least that dimension. I'm not 100% sure whether you can have like a sequence of closed sets with increasing dimension, but no closed subset with exactly the same dimension. That I'm not sure. But yeah, but like the fact that closed subsets with arbitrarily large dimension follows from the fact that Fourier dimension is defined by means of probability measure and the support of a measure is closed.
But it's not clear, like whether what you get for the Fourier dimension and what you get for the Hausdorff dimension, whether sort of these guys need to happen,
yeah,
like at the same place, or whether
yeah, exactly.
Thanks.
Okay, are there any other questions?
Hi, it's Maria. I have a question. So, Manlio, on your last proof, is it essential that you build a Salem set, or was that just an added bonus?
No, it's not essential, but it's free, let's say.
I see.
Like the point is that the way you build a set is pretty much just using the construction we made for the previous proofs, and in that proofs, yeah, it's actually free, right? You can, if you want, you can make it in such a way that only the Fourier dimension answers your questions and not the Hausdorff dimension, but that would be artificial, right? If you have for free a way to make it in such a way that both Hausdorff and Fourier dimension like are the same. So yeah.
Got it. Thanks.
Okay, any further questions? So perhaps I have one question. So you have kind of presented these results as if they are independent. I mean, the classifications of the Borel complexity of these sets and the Weihrauch complexity of these maps. So do you think there's a more generic relation between such results? I mean, that you can derive one complexity from the other? Is there any relation?
I'm not sure I understand the question. Like what do you have in mind?
Okay, if you have a map which is Weihrauch complete, so to say, or equivalent to some composition of limits, and then you look at the sets defined by these inequalities, I mean, can you move somehow from one side to the other? So are these completely independent results, or is there any relation?
I don't know. I never thought about it in that way. So
if I may, as a co-author,
Sure.
Alberto, hi.
Sure.
I managed to switch off my audio when I was started speaking. Okay, I think I'm online now. So we actually got from one side to another. We got from the descriptive set theory to the effective descriptive. This was our path. from the descriptive set theory to the effective descriptive set theory, and eventually to the Weihrauch degrees. Obviously, if you can prove this result, which is on the slide now, by way of Weihrauch reducibility without making any sort of appeal to the complexity, which is what we are doing for the first sort of easy direction, the first direction, the less than or equal W, here less than or equal Weihrauch, then you could go back and show that some sets are also sigma 0 free complete or something like that. They are effectively sigma 0 free complete, and so they are also bold-face sigma 0 free complete, I believe. I mean, you could also move the other direction, but you need to have a way of proving this result without resorting to that kind of results. I mean, obviously there is it can be a two-way road, but we sort of traveled the road one way, and it's possible maybe to travel the other way, but obviously you have to start from our point of arrival. And then obviously, I don't think these results will tell you anything about the Salem sets, actually. It will give you something about the computation of a Fourier dimension, but not about the Salem sets, because these are connecting actually two different dimensions, which may happen to be the same or not the same, depending on the actual set you're looking at.
Okay, thank you. So if there are no further questions, then let's thank the speaker again. So many thanks for your nice talk. I will stop the recording.